Okay, so we better get going. It's 1 minute past, and it's maybe it's going to be quite dense. So for those of you who didn't see me last week, my name's Paul Verbic. I'm going to be teaching the computer algebra module for this class. Last week we just sort of shot the shit and talked a little bit about the industry, my experience in it, and like the fundamentals of the discipline. Today we're actually going to start getting into the nitty-gritty. Now, you've all sort of managed to download and start sort of dealing with the project a little bit. I'm struggling a little bit, but at least you got your hands dirty, I hope. So like the philosophy behind this project is to sort of like simulate industry, right? Like there's a version of this project where we could have given you something very clear, like an extremely clear spec with a framework in it that was very clear to fill in, and I just give you pseudocode and then you execute it. Now, in truth, industry has been contacting us saying, your students or students generally don't seem to have the ability to cope with like non-specific specifications, just like sort of fuzzy type of instructions, like improve this or test this. So what Yanni and I are trying to do is like simulate industry by saying, here's like a package. It's not very well documented. It may not even be that well implemented, but you need to go into it and nonetheless understand it and improve parts of it. So it's sort of deliberately confusing in some senses, just to get you sort of comfortable with, you know, what the real world is going to be like. But that being said, of course, me and Yanni are going to be here to help fix any confusion. Okay, so what's going to happen now is I have 3 hours this week and another 2 next week. So what Yanni would like me to do is get through all of the material today and tomorrow so you comprehensively have it, right? So you could technically do the entire project. Now, it's going to go quite fast, right? So the idea is I'm going to go through it all. You may have to like take the weekend to absorb it a bit, and then we're going to come together again on Monday, at which point you should have like tons of questions and issues. Where we'll be here, me and Yanni, to help you work through those issues. So let's just get to it. And please, just at any point, if you don't understand something or if you want me to clarify something, just stop me. Last year, I sort of made the mistake of like assuming too much background knowledge. And it does seem to be the case that for some, this will be a review, and for some, this will be brand new. So I'm just going to go ahead and make the assumption that this is going to be brand new for everyone. So don't be offended if I'm explaining something that you understand quite well. So just to sort of summarize in like one sentence what we talked about last week, the main difference between a computer algebra system and a numerical system is that a computer algebra system has the capacity of representing algebraic numbers. That is, those numbers that are roots of polynomials with integer coefficients. And the way that we manipulate algebraic numbers is by polynomial arithmetic. In particular, doing polynomial division or executing the remainder algorithm is equivalent to evaluation. So what we have to do today is establish that a polynomial ring with coefficients that are form a field, that is an integral domain, and furthermore, a Euclidean domain. That is, we're going to be able to have GCDs and a division algorithm. So what we're going to do is go through integers first, talk about how integers are an integral domain and a Euclidean domain. But you should always keep an eye to the horizon, thinking that everything that we're going to do with integers, we're going to repeat with polynomials, right? Because they're just sort of different ways of representing numbers. So if this initial stuff seems trivial, just keep thinking then in the back of your mind, how then are we going to dump in polynomials? And how is that going to make sense in that context? Okay, so these are the rings of polynomials. R here is any type of ring. And then we sort of use these square brackets X to generate the following set. And that is all finite sums, k goes to 0 to n of ak to the xk, where this is called a term, this is called the coefficient, this is called the indeterminate, and that is the degree of the indeterminate. So n are the natural numbers, and this is always fun. Who thinks the natural number should include 0? 1, 2, who doesn't? Yeah, it turns out the inclusion of 0 in the natural numbers is kind of a cultural thing. So it's always surprising to see which cultures included and which cultures excluded. So I always thought that the naturals include 0. We have a different symbol, the whole numbers. would start counting from 1. But in any case, for this presentation, we're going to include 0 in the natural numbers. We're going to use this Z to represent the integers. That's all the natural numbers plus the negation of those natural numbers, but we don't represent 0 twice, right? There's no negative 0. And we're going to let this blackboard P be the set of odd primes. That is all the primes excluding 2, because funny things happen with the prime 2. Can anyone tell me what a group is? Yes. Yeah, essentially. So a group basically is a collection of items for which you can basically define addition over that collection of items. And you should have a 0 in that set, and you should have some type of additive inverse in that set. A ring is an extension to a group where, in addition to getting addition, you also have a multiplication operator. So here are the ring axioms. So a ring, which we denote like this, R plus, a ring, which we denote R, has to form a group with addition, right? So the ring and a plus is an abelian group where the addition operator has to be associative and commutative. Commutative means A plus B is the same thing as B plus A, and associative basically means you can bracket in whatever manner you choose, and it doesn't matter. There has to be an element called the additive inverse. So for every A in the ring, there should be some B such that A plus B is A, right? So this is, did I say inverse or identity? There should be an additive identity. So there should be something that's acting like the 0. And there should also be, for every element in the ring, that ring should have an inverse. So there should be, for every A, a B, so that A plus B is equal to 0. Okay, let's think of a real example here. We're all familiar with like clock arithmetic. If I were to say 11 plus 3, that's going to get you 2 o'clock. Okay, so let's just designate 12 as 0 o'clock. So is that a group? Why not? Then tell me which one of these points it violates. Right? If we add 3 o'clock plus 2 o'clock, is it the same thing as adding 2 o'clock plus 3 o'clock? I think also associativity is going to hold. Is there some type of additive identity? Is there like a hour on the clock by which I add and it doesn't change anything? What's 2 o'clock plus 12 hours? 2 o'clock, right? So it does seem that there's a 0 on it. Is there additive inverses? What do I have to add to 2 to get 0? 10. Okay, so it does seem that like a clock with 12 hours on it does form an additive group. This R and the product has to form a monoid. That is to say that you have to have an associative multiplication operator, and there has to be a multiplicative identity. That is to say there has to be some element in the group which is acting like the 1. And we also need that multiplication distributes over addition in the following ways. And if these things hold, then the ring with its plus and its product form this set with a plus and a product form a ring, right? So it's essentially a group with addition and multiplication. So here's some examples of some rings. So this is the trivial ring. If you just take the set 0, that trivially satisfies all of the properties above, right? We can go through, but I don't think there's much point. Why don't the natural numbers form a ring? Well, I guess I put the answer there, right? There are no negatives in it, right? So what number do you have to add to 3 in order to get 1 back or 0 back, right? There is none. And arithmetic on the clock does form a ring, but it won't form a field, which is the next thing we're going to talk about. So just some more terminology here. A 0 divisor is an element in the ring, which has another element that you can multiply by where you get 0, which is kind of strange, right? If you work in a ring, you can multiply 2 non-zero elements to get a 0 element. And that has really strange consequences. So if I'm on the clock of 12 hours, is 3 a 0 divisor? Why? 3 times 4 is 12. And so 3 is a 0 divisor and 4 is a 0 divisor. And it's just kind of strange that you can produce the 0 without involving the 0. Right? So we're going to avoid rings that have 0 divisors in them. So an integral domain is a non-zero commutative ring without 0 divisors. So we're more interested in these integral domains, like restricting the type of rings that we're going to work with. So we're interested in rings that don't have these weird zero divisors and they can't just be like the trivial zero ring. So the integers form an integral domain, integer, integral. Clock arithmetic does not form an integral domain because, as you said, 3 times 4 is 12, right? So there's the presence of zero divisors. We're mostly going to be interested in these fields, and this is a ring with the extra provision that every element in the ring also has a multiplicative inverse. So does the clock form a field? Why? Yeah, so there's nothing that we can multiply 10 by, well, not 12, 1. Yes, to get the unit back. Some of the elements you can multiply by to get 1. Let's think if we can think of one. What multiplies out to 13 or 26? I can't think of one. I have examples later on. This is why I don't do things off the cuff. But it turns out if you let the number of hours on that clock be a prime number of hours, then you will generate a field in that case. The most basic example for a field is that of the rationals, right? All of the fractions. What is the inverse of A over B? B over A, right? So you really trivially get inverses over the rational numbers. Okay, so now we're going to go through all of the arithmetic that you learned in elementary school or high school and like demonstrate the mathematics that lies behind them, which you may have never thought about. Again, for the purposes of saying we're eventually going to have to extend all of these ideas and algorithms to work over the integral domain of polynomials with coefficients from fields. So here's the division algorithm, right? So this is a theorem. So for any two integers, so that the b is positive, there's a unique quotient and remainder satisfying this expression, right? A is equal to b times q plus r, right? So a is some quotient times so we have a numerator and denominator, and the numerator is equal to the denominator times the quotient plus some remainder. Here's an example. If A is 23 and B is 7, so I just have to remember to execute these things, then in Julia, this division operator, which you get by doing /div and hitting tab, gives you 3. So that's going to be the quotient of this, and R is going to be the remainder, which you use this percent sign to get, right? So it's true that 23 is equal to 7 times 3 plus 2. Okay, well, this is a theorem, right? If I'm stating that it is the case that these numbers exist, how can we prove that? So I was talking a little bit last week about the one of the laboratories I worked in was the Center for Experimental and Constructional Mathematics. So you're familiar with constructional proofs? So we just have to construct B and R. If I give you some method or algorithm for constructing B and R and then demonstrate that they have these properties, we've proved it. So the proof of this is actually, here's the remainder algorithm. Here's long division. And long division is going to produce that quotient in the remainder. And then we could go and do some like extra proving to demonstrate that it actually satisfies the conditions that I claim that they satisfy. So let's just look over the basic remainder algorithm, and we'll go over some of the Julia features as well. So here's a remainder. Have we talked about this in this class, like what it means to work with these abstract types? A little bit? Okay, because I want this remainder to work on anything that like works like an integer. And we have like big ints, and we have like signed ints and unsigned ints. So essentially what this is saying is this remainder algorithm is going to work on input where A and B are type T, but T is like some concrete type derived from like this super type of the integer. It's like T is anything that acts like an integer. So I'm telling Julia, like, this is going to work on any type which acts like an integer, rather than having to define this like 5 times, right? For big ints, right? For machine ints and so on and so forth, because it's just going to be the exact same set of instructions. So here's like a cheeky way of like having an if statement, which exploits the fact that AND short circuits. You could read this as if A is less than 0, then return this, right? Because the only way this is going to trigger is if this is true. Because if the first part of this conjunction was false, then short circuiting wouldn't execute this. So we do this a lot, right? It's just like a fun way of getting like an inline if statement. But this is all the remainder algorithm does. If you give me A and B, as long as A is greater than or if A is less than or equal to 0, then I just rerun the remainder algorithm to make it positive. So if we get to here, we can presume that both A and B are positive. And then we just turn the remainder of A minus B. Like the remaindering is essentially just removing the denominator like as many times as you can until the last time you remove it, you hit a negative number. And the same thing's going to apply when we start working with polynomials. So we should note that there's a built-in remainder, of course. So this one's R is the one that we defined up there. This is the built-in one, which actually acts the same way as like this percentage operation. And they all satisfy this property, right? 23 minus the quotient of 23 by 7. Well, this is just saying 23 minus 23 quotient by 7 times 7 is like, there's an invariance there. Here's just some other examples. Like what is the remainder of 15 when you remove 5, 0? What's the remainder of 4 when you remove 101? Well, it's 4. You can remove 0 101s from 4. What's the remainder if you do 125 divided by 4? Well, there's some quotient, I don't know, but at the end you get 1, right? Just to demonstrate that it's there. The quotient algorithm is just sort of like the converse of the remainder algorithm, very similar. It has the same typing up here where we're saying, look, I want the input to be anything that acts like an integer. I don't want to have to define this like 5 or 6 times for every type of integer in the system. I can run that. I'll just show you that it's working. How many times does 5 go into 15? 3. And in this case, it's remainder 0. How many times does 101 go into 4? Well, 0 times. How many times does 4 go into 125? Well, 31 times. So here we can just utilize Julia's print formatter, which is a little bit different than you're seeing in Python. If you want to do a formatted print, you just use these $signs, and that's equivalent to the just dumping in the actual value of A rather than printing $A. So what are we doing here? Let's just see. So we have A and B. We're going to take out of these tuples, and we're just going to demonstrate that we can find a quotient and a remainder that satisfies this expression, which is the thing that the theorem was guaranteeing. There we go. So 15 is 3 times 5 plus 0. 4 is 0 times 101 plus 4. 125 is 31 times 4 plus 1. Nothing surprising yet. Okay, of course, in Julia, we have this percent and division, so you should use them. You don't really have to use these quotient and remainders that we defined. You should note that if you're from Python, you may be used to using double slash as integer division, which is not the case in Julia. Double slash in Julia gives you the rational type. So indeed, we could have worked with fractions. Like Julia does implement fractions. We're just going to like pretend that they're not there for the purposes of this. But it does allow me to express the remainder algorithm in kind of a different way. So this expression, if you like divide through by 7, you get an expression like this, right? So the division algorithm gives you a quotient remainder the same way that if you were given a, would you guys call this an improper fraction here? Okay, so like this is an improper fraction, and we sometimes learn how to write them as proper fractions, right? Which is like the integer piece and the fraction piece. And we're going to be duplicating exactly this when it comes to polynomials. You may have done this in calculus when you've done synthetic division, when you're doing partial fraction expansion. Yeah, you need to do some integral of some rational polynomial, but the polynomial's numerator has higher degree than the denominator. So the first step is to sort of do this by doing one step of synthetic division. Okay, so we're going to give you sort of a crash course in all of the number theory that's going to be pertinent for working in fields specifically. So some more notation here. So I'm going to say the sets Z with the subscript n are going to be a finite many of the integers, specifically 0 through n minus 1. And these are called residue classes when an addition and multiplication are done modulo n. So you're familiar with this modulo n? So whenever you see modulo n, you can just think of remainder after dividing through by n, right? So the residue class on the clock, right? You have 3, but you also have 15, and then 27, and then 39, right? All of those numbers exist in the same residue class. And it just so happens that 3 is like there's this strange word in math that I don't really like. Have you heard the word canonical? Canonical means loosely like the standard representation of like the residue class, right? So although 3 and 15 are like equivalent on the clock, we would never say like 37 o'clock, right? Because that standardizes to 3, right? We prefer using the canonical representative of the residue class. Okay. Hope. Did we lose something? Okay, so here's some like notation. I'm going to say A is congruent to B mod C when A remainder C gives you B. Right, so this is just a better way of writing the remainder. So I can say something like 13 o'clock is congruent to 1 mod 12. That's how that works. And you've already seen like this type of sort of remainder arithmetic already, because the integers that you're currently working with aren't all of the integers. Right? This is one of the things that we're going to have to cope with in symbolic computation. Like we really do need to use all of the integers of arbitrary size. What we're working with are like the integers. Well, we have 2 to the power of 64, many of them. So we can either have 0 to the power of 264 minus 1, or we can cut that in half to get some negatives. But this overflow, it's not really incorrect. Sort of that's important to understand. So consider this, like suppose we're working with the 8-bit integers, positives only, right? That means you have the numbers 0 through 265. If you were to add, so here's 2 to the power of 8 minus 3, that's what, like 252, 60, it doesn't really matter. 2 to the power of 8 minus 3. And if I add to that number 4, what are you going to expect to get back? Yeah, 1. And why does that make sense? Or how can we make sense out of this? Yeah, I understand that we're getting overflow here. Like that's the technical explanation. But what's like the theoretical explanation of this? Yeah, what we're working in is effectively the integers mod to the power 2 to the 8. Right? So this is perfectly, like this isn't really wrong. Right? It's wrong if you're thinking that you're expecting to get 256. But if you know that, oh, I only have a finitely many numbers, and thereby when I go off the end, I have to go back to the beginning, right? We're really working with remainders here. This is perfectly valid as an arithmetic. That's what I want to show you here, right? Like if I were to take 2 to the power of 8 minus 3 and add 4, and then remainder out by the 2 to the power of 8, you're going to get 1. Right, so this is perfectly valid arithmetic if you're working in sort of one of these residue classes where you're only given a finitely many amount of integers. So overflow isn't wrong. It's you just are just working in a different ring than the generic integers. Sorry, guys, I still have sort of a sore throat, so bear with me. Okay. There's also this notion of the symmetric mod. We may want to use negative numbers. So suppose we have 0 through 6, right? That would be working mod 7. We can also work from -3 to +3, right? Those are also 7 numbers. And this is called the symmetric mod rather than the mod. So in the symmetric mod, instead of having 5, you're going to have -2, right? And you do it like this, like 0, 1, 2, 3, 4, 5 gets you -2. It's really easy to convert back, right? 7 minus 2 gives you 5. Right? So that's how you get to and from the symmetric mod, right? So mathematically, it doesn't really matter. We can have the negatives or we don't have to have them. When you're programming, though, this becomes relevant. Right? So if we want you to return something with negatives, which we will when we're doing Chinese remainder theorem, you're going to have to do a symmetric mod as your last step, not a mod. But in terms of like my presentation, it's not really going to make a difference. So I'm going to use mod to mean symmetric mod when I want it to and not when it doesn't. Because it doesn't matter. These are just, we're just swapping out the canonical representative for that residue class, right? Instead of saying, oh, -3, the mod one would have its standard representative before. Okay, so let's start looking at some of the arithmetic that comes out of working with finitely many integers rather than all of them. So we can come up with these addition tables, right? So here's Z6, it's all the numbers 0 through 5. Have you seen this yet? Good, what is it called? yeah, a unit range, right? So these are going to give you a range of numbers 0 through 5. And I'm going to just take A and build this matrix, which is going to be like the addition table. Okay, so what do we see here? So this is like a multiplication table, but for addition. So this is what you get when you add 1 and 1. This is what you get when you add 2 and 1. And you see that this is symmetric in terms of a matrix. That is, it's equal to its transpose. And this can only happen when the operator that you're using is commutative. So this could be one of the ways that you check properties of your ring, right? You just generate its addition table, ask if it's symmetric, and if it's not, you're not working in a ring. You can see that the additive identity is 0, right? Because this row is invariant and this column is invariant, right? So adding 0 to anything on the left or on the right is not going to change anything. And you all can also see that each column and row has a 0, and thereby each element has an additive inverse, right? So if I look here, there's a 0. So that means the additive inverse of 4 is 2. Right? That makes sense, right? Because we're working mod 6, 4 plus 2, mod 6 is 0. Here's a neat thing. So here I'm going to print all of the additive inverses. The additive inverse of 0 is 0. The additive inverse of 1 of 5 is 1. The additive inverse of 1 is 5, 2 is 4, 3, and so on. I think we should parse this because it's kind of interesting. Would anyone be able to read this or tell me how it's working? I'm going to try doing a little bit of Julia as we do some of this theory. Yes. Okay, so let's start with this. What is this going to give? Right, a Boolean matrix, right? So it's saying this is the occurrence of 0 in that column, and it now contains a 1. And then find first is going to find the first non-zero entry, and then we're just going to do that for all of the columns. It may not be the best way of doing it, but that's how you can parse that out. Okay, so we've done the addition table. Now let's do the multiplication table. So I'm just going to spin up the same thing. And what can we see here? Well, there's the 0 multiplying stuff by 0 on the left. This is multiplying by 0 on the right. And we can see that some of these columns have 1s. So what does that mean? So this is 0, this is 5. So this means that 5 times 5 is 1, mod 6. Is that true? How many times? What is the remainder of 25 when you divide out by 6? 1. Okay. What's another way that we can make sense of this, given that we talked a little bit about the symmetric mod? What is 5 mod 6 if we're using the symmetric mod? -1. 5 is -1 mod 6, right? If we're using the symmetric mod. Therefore, it's no surprise that -1 times -1 gives you 1 back, right? This is sort of like the -1 squared. So it's true that 5 or -1 has an inverse, 1 trivially has an inverse, but none of the other elements have inverses. If they did, we would be able to find 1s in these columns. So therefore, this, like Z6, does not form a field. Right? There are elements in it that do not have an inverse. Worse yet, there's the presence of 0 divisors, which like are bad, right? But when you produce zeros without involving 0, like things really are get really confusing. So we're not going to use sort of these types of sets, right? What we're going to do instead is use these sets so that the number of elements in them are prime, right? So we're going to use, I think that should be 0 through 4, not, okay, I'm going to just change this. Sorry about that. All right, we're going to use 0 through 4. There are 5 elements in there, so we're going to use sets which have a prime number of elements in them, and these are going to be fields. So we're going to just go through the same multiplication table. And what do you see now? Okay, so obviously 0 doesn't have an inverse, right? That's the exception. Anything multiplied by 0 is 0. Right, so not accounting for that. Can we find a 1 in every other column? Okay, so let's use this chart to figure out what the inverse of 3 is. So 0, 1, 2, 3. And then the 1 is here. So this means that 3 times 0, 1, 3 times 2 should be 1 mod 5. Is that true? 6 mod 5 is 1? Cool. Okay, so here we can, each of these elements has an inverse in this table, and thereby the ring Z5 is a field, right? So everything is invertible. GCDs. Okay, so the greatest common divisor is a very fundamental operation in computer algebra. Last week we talked about why. And when we take the GCD of two polynomials, what it is in effect doing is giving us the common roots of a set of stuff, right? So GCD enables us to find out where surfaces in space like pass through each other. So it's more than just doing a GCD. This is its statement on the integers, right? So if you give me two integers a and b, both of them can't be 0. We designate g, an integer, as the greatest common divisor of a and b, and we denote that GCD of a and b when the following three things hold. You familiar with this division symbol or divides? Okay, good. So g divides a and g divides b, right? That means g is a common divisor of both. That's the first thing that it has to be. If h divides a and h divides b, h has to divide g. This is just sort of the mathematical way of saying like g is the biggest divisor of a and b that you can find. And g has to be positive. Doesn't really have to be positive, but we're going to make it positive just so we can have a unique GCD rather than saying we have the positive version and the negative version. So this is just to standardize things. So the GCD of 6 and 4 is the GCD of 2 times 3 and 2 times 2. So you can find the greatest common divisor in here is 2. The GCD of 6 and 0 is 6. And it's for this reason, right? It's because this is basically saying you have the GCD of 1 and 6 and 0 times 6, right? So you're always going to be able to pull off that, like anything divides 0. So what's the biggest thing that divides the non-zero thing? Well, itself. So you're going to get 6 back. So this is just important, right? Not both can't be 0, but one of them can be 0. And when one of them is 0, the GCD is just the other thing. And this will become important once we start writing algorithms, right? Because the GCD algorithm is recursive. And eventually we're going to want to hit some type of base case, like where one of the inputs is 0 or one of the inputs is 1, and we can make some type of conclusion. So there's a built-in GCD function like this. A lot of effort has likely gone into it to making it fast, but we're going to make our own soon as well. I'm just going to show you how to like use the base GCD and show you some other cool Julia features. So what does this mean? Oh. So this says give me 5 random numbers generated between 1 and 100 uniformly. And then this multiplication in these ellipses means multiply them all. So this is going to give me the product of 5 random numbers. This is going to give me the product of 5 random numbers. And then I'm just going to ask for what their GCD is and hope that we do get some GCD. Okay, so 200, 261. I can go ahead and change the seed and we can get another one. Oh, geez. Interesting question. Like, what is the probability that this was not going to be a unit? That would be an interesting question that we're not going to address today. Any of you heard of Euclid's algorithm? Okay, so Euclid's algorithm is the algorithm which gives you the GCD, which is very important. We figured at some point in time, like we didn't have a division algorithm. We didn't have a way of finding. Someone had to like determine this. We could easily define these properties, but actually finding that number, you know, that requires some thought. So it turns out that the GCD algorithm or the GCD satisfies the following properties. And from these properties, we can just deduce an algorithm from that. So the importance of the Euclidean algorithm. So if you have a ring and that ring admits the Euclidean algorithm, that is, we can do the Euclidean algorithm within that ring, then the ring becomes a Euclidean domain. And we're going to go through great effort to demonstrate that the polynomial ring, when coefficients are taken over a residue class, in fact is a Euclidean domain, right? So we can do things like have remainders and GCDs over it. Okay, so these 3 properties, so GCD of B and A is the same thing as the GCD of A and B, obvious. The GCD of A and B is equal to the GCD of A remainder B, which is kind of cool, right? Because now R is necessarily going to be smaller, right, than A, which is great for like algorithm purposes. You always want to like drive one of the inputs down, right? You need to descend till you eventually hit some base case. And finally, the GCD of A and B is equal to the GCD of A minus BB, right? That you're just sort of taking out 1b from A. So it shouldn't really affect anything. So here's the algorithm, and you can just do it in 2 lines, right? So I said if B is 0, then you just return A, right? The GCD of A and 0 is A. Otherwise, you just sort of combined rule 1 and 2, and you can just make this recursive call, right? Sort of permute the input and take the remainder. So one of these inputs is necessarily going to go down, and at some point, one of this calculation will have to at some point give you 0. Because if it doesn't give you 0 here, what did that mean? That means that A had to be smaller than B. But when you switch the inputs then at the next call, then this is going to be the opposite, right? You're going to have A has to be bigger than B, which will definitely give you a 0 back on that remainder. Jeez. So in any case, it's in base. So you should be using this one, not really this one, because the base one's going to be way faster. But it's really simple algorithm to implement. It's like a really beautiful algorithm. And any ring that allows for this is going to be called the Euclidean domain. Extended Euclid's algorithm. So in addition to getting the GCD, we can also generate these things called the Bezout coefficients. And if you recall last week, I said my main contribution to science was effectively adding the numbers in front of those regular chains, and those are also called Bezout coefficients. This is sort of simpler than that, but what it allows us to do is if you give me 2 integers, the extended Euclidean algorithm allows me to write them as a linear combination of one another. Right, so given A and B, I can always form some expression, A times S plus B times T is equal to the GCD of A and B. And this is going to be critical, right? Because I'm going to want to actually have an algorithm for deducing inverses in fields without having to generate a multiplication table and linearly trying to find it. That would be a disaster. Okay, so what does this mean? Suppose that we have the extended Euclidean algorithm, which I've defined here. It's not overly important that we study it. You just sort of have to believe me that it does give what it wants. And there's some usage examples just to sort of try and convince you that it is working. It's not too hard to prove it. It would take way more time than we have today. But suppose the extended Euclidean algorithm, in fact, gives you this S, T, and G. What is the consequence here? How can we utilize this to generate inverses, do you think? Any ideas? Okay, so I'm working mod 5, and I want to find the inverse of 3. How could we use the extended Euclidean algorithm to do that? Okay, let's look. Okay, so I'm saying that the extended Euclidean algorithm gives me S and T that satisfies this property. Let's take this expression and let's reduce it modulo M and see what happens, right? So I'm taking the GCD of A and M here. So if I take that expression modulo M, I know that the GCD of A and M is congruent to A times S plus M times T mod M. But what is M times T mod M? 0, right? Because it's M times T is a multiple of M, and thereby remaindering by M is going to give you 0. Okay, so that means that we have an S so that the GCD of A and M is congruent to A times S mod M, which gives us the GCD of A and M is congruent to A times S. What's the last thing that we need to do here? I'm searching for an inverse for A, which means I'm looking for some other number so that I can multiply A and get 1 back. So what does this need to be? How can I make it 1? Yeah, but yes, they have to be coprime, but how can I assure that they're coprime? What can I select for M, knowing nothing about A? A prime, any prime. So if I make M some prime, we know that GCD of A and that prime is going to be 1. And therefore, we have an expression here that actually says A times S mod prime, right, is equal to 1. So what in fact the extended Euclidean algorithm has permitted was for us to find inverses in residue classes of prime characteristic, like these ZPs. Right? So this is very important, right? Because now we can generate inverses fast, like way faster than just like looking through a table. So here's how we can find the inverse of 5 mod 13. Right, so I say, here's my A, here's my M. They're co-prime. It has to be. M is a prime. I run the extended Euclidean algorithm and I get this out. So that's the GCD, and those are the Bézier coefficients. We've made a new definition in your project called inverse mod, basically to just like kick out that 1. Oh, semicolon shouldn't be there. Okay, so I just take, I'm saying I is the inverse of A and M. So I is the inverse of 5 mod 13. So it says 8 is the inverse of 5 mod 13. Now let's just check that. So this should be 8 times 5 mod 13 is 1. Okay, so when I say inverse, you think I can use the extended Euclidean algorithm to get that. And furthermore, we're going to do the same thing on polynomials. Right? That's always the thing that we have in the back of our mind, right? Why am I showing all this trivial stuff? Well, because I'm saying it's going to work over any Euclidean domain. And we're going to introduce a more complicated Euclidean domain in due time. Chinese remaindering. So this is a very powerful piece of technology in the discipline of symbolic computation. And you should be interested in it because it's explicitly one of your tasks. Sort of now you should perk up because I'm going to tell you how to do some of your homework. So the problem in symbolic computation is that we're going to be generating extremely large integers. And furthermore, all of the algorithms that we're talking about have to work over a field. And the polynomial rings in their natural state certainly don't form a field, right? So we're going to have to like make them form a field by restricting the coefficients to these residue classes of prime characteristic. So what we're going to do in your multiplication problem, for example, is compute the product like mod 3, mod 7, mod 11, and then use the Chinese remainder theorem to like lift those solutions back into the integers. Okay, so this is the Chinese remainder theorem on integers, and then we're going to extend it to work over polynomials. So are any of you familiar with the Chinese remainder algorithm yet? No, some yes. It's surely if you took a number theory class, they would definitely show you this. But it works like this. It's suppose I have like a secret number, and you can ask me what that number remainder is, mod whatever you want, right? So I say, okay, look, I have a secret number. It's 19, and I'm going to tell you that it's 4 mod 5 and 5 mod 7. Can you then reconstruct the number 19, like without sort of just going up all the integers and testing, right? It has to be faster than the naive way. And the answer is yes. And we can do this via Chinese remaindering. So here's how we set up the problem. So U is like the secret number that we want to recover. U1 through UK are the images, like are all the remainders. And M1 through MK are all the things that we're taking the remainder by, right? So U is congruent to U1 mod M1. Another way of saying that is U remainder M1 gives you U1. So the statement says find U, and this is the theorem, right? So this is how it always works in constructional mathematics. We're saying, yeah, the solution exists. That's the theorem. And then the proof is me giving you an algorithm to actually construct it. So if you give me M, and M is the product of all of the little m's, the statement of the Chinese remainder theorem states that there's a unique U between 0 and M minus 1, right, that finite slice of integers, such that this U is that magic secret number, right? It has the property that U is congruent to UI mod MI for 1 through K. Okay, so let me show you how we can construct this. It's actually it's interesting and it's not that difficult. Okay, I'm just going to say this is U. U is this number. And can you see that this number has all of the properties that we're talking about? So let's study this. So U is going to be V1 plus V2 times M1 plus V3 times M1 N2, right? And so on and so forth. So that this VK plus 1 is being multiplied by like all of the M's, right? Where M's are all of the things we're remaindering out by. Look at this number and look what happens if I reduce it modulo MJ. That means that like we get non-zero terms up to mj minus, up to vj, and everything afterwards is 0. Right? That's going to happen for like any mj we take. Okay, so what happens then if I take m1, like modulo m1? All of these terms disappear except for v1. And then I can recover v1 quite easily. I can actually like get that term. Then once I have v1, I can put that into u2, right, and solve this, right? It's like the first two things here. And then I have v1 and v2, and then I can recover v3, which is the next three things there. And do you see that this is going to satisfy like all of the initial conditions? Yeah, okay, so there it is, right? This is the Chinese remainder theorem, and that's how you construct it, essentially by just undertaking, right, these steps. So that's the proof of its existence. If you want to prove it's unique, it's a little bit more tricky. I can leave that up to you. But here's some code, right? Suppose I say that U is congruent to 2 mod 3 and 1 mod 5 and 5 mod 7, right? This is how you can construct the U, right, among the integers, like the secret one. So here's all the UIs, where you can get this subscript by going /tab. That's sort of one of the benefits of using Julia, is that you can use subscripts in Unicode. So here are all the U's, here are all the M's. We're just going to start filling a vector of these V's. So I'm saying V1 is just equal to U1 at 1. And then I take that U1 of 1 and I back substitute. Right, we have to look at here. So we're going to have to sort of do these inverses, right? Mod M2. But that shouldn't trouble us anymore because we know how to do inverses now in these residue classes using the extended Euclidean algorithm. Right, so we just use the extended Euclidean algorithm to recover, and then we find V2, and then we just keep moving back up that chain. And we take this inverse mod of now the next one up, and then at the very end, we got this U, which is definitely going to satisfy the initial conditions, right? Because if I take this mod M1, we get V1 back. If we take it mod M2, we're just going to get these two things back. And you can see if I just go through and print, let's verify. So we needed to find numbers that were 2 mod 3, 1 mod 5, and 5 mod 7. So is 26 congruent to 2 mod 3? How many times does 3 go into 26? 12 times? And then, is that correct? 3, 6, 9, 12, 15, 18, 20, 24, right? Then we have 2 left over. How many times does 5 go into 26? Well, 5 times, let remainder 1. How many times does 7 go into 26? That's 3 times, and we got 5 left over, right? So this routine faithfully returned that like secret U. Okay, so you could study this a bit, but the point is that if I give you a set of images and a set of sort of what they're being modded out by, you can recover like a number in the integers, right? That will give you the property that when you mod out by each of these individual things, it gives you the UI. Right? That's okay. So this is your, oh, not yet. Okay. So just keep this in mind that we've in fact like have implemented a integer Chinese remainder theorem, because we're going to extend that soon to using polynomials. Okay, so now we're going to like stop talking about integers because that may have been trivial and start now talking about like the actual thing that you're working with in these polynomials. So by this point in your mathematics career, you have surely worked with polynomials. A polynomial is something like x squared plus 2x plus 1, but not like x squared plus 1 over x minus 1. This is a rational polynomial. And it's also not something like x sine x. Does anyone know what, like, where the class of sort of sine x and tan and fall into? Like not just trig functions, but like all the things that aren't polynomials are rational polynomials. Ever heard of this? Special functions? It's like basically anything that you have to look up in a table to integrate, right, is designated as a special function. Okay, so let's define our polynomial ring and let's convince ourselves that it is indeed a ring. So let R be a ring, and we say A is in the polynomial ring, right, of Rx, but it looks something like this, right? This is the generic polynomial that you've been used to working with. It has terms an xn, or generically ak xk. And one of them is the leading term, right? This one. And so the leading term is the term of largest degree, which also has a non-zero coefficient. Like this gets tricky because, well, okay, with this provision, with saying an can't be equal to 0, right? That means the leading term has to be here, but we don't really need to have this, right? Like we can have an infinite amount of 0 terms. That doesn't really trouble us theoretically. But in order to, then we would have to designate the leading term as something with non-zero coefficient, right? I wouldn't say that the degree of x squared plus 1 is 4 because I can technically have 0 times x to the 4 in front of it. That's sort of nonsensical. Okay, so a is called a polynomial in x, and ak, xk are its terms. The degree of a is n because this is non-zero. The leading coefficient is the a on the leading term. So that would be an, and the leading term is an xn, right? So you have the x to the power of k's, those are called monomials. You have their coefficients, these are the ak's, and their products are called terms. So in effect, like a polynomial is just a sum of terms, right? And this is important in terms of its implementation. There are some conventions here. The zero polynomial requires special consideration. Right, so for one, we should decide like what is the zero polynomial, and that should be the polynomial whose term is 0 times x to the 0. It could have been anything, right? It could have been any term with a 0 coefficient, but like that's going to make implementation kind of strange, right? So we designate 0 times x to the 0 as like what 0 is. So by convention, the leading coefficient of 0 is equal to the leading term of 0, which is 0. And maybe more puzzling, we're going to designate the degree of 0 to be minus infinity. Right? Like we don't really want it to be 1. It's kind of like 0 is not really anything, right? So I'm uncomfortable saying that it has any degree. It's not really a constant in terms of a polynomial. So this just helps with the theory. So here's how a term is being represented in your project. Hopefully you've taken a look at this. There is a previous version of your project which says that your polynomial should be a list of tuples. That was kind of a little bit wrong. Like these terms in effect are storing tuples, but your polynomial should be like list of terms because we've defined a bunch of term arithmetic, like what you want to be able to exploit. So if you're putting tuples, you would have to sort of duplicate all of the term arithmetic. So please note that change. Here's the 0 term. Right? And the polynomial is the polynomial with that as its only term. And sort of here's a constant term. So for any questions about like how this term structure was created or its usage or anything like that. Okay, so you've probably already been grappling with it. This is the polynomial type that exists in our project currently, which is what we want you to change. Right? Because this is holding things dense. Right? For example, here, right? This is going to contain all of the it's going to contain 0 terms in all the places where there should be a 0 term, because this is going to be a list of length k plus 1 to hold a polynomial of degree k. And this is sort of useful because to add polynomials together, you just need to do a vector addition. But it's going to be super bad for us because we're going to have to use polynomials like x to the power of n minus 1, for which this is like the least dense polynomial you could possibly create. And we're going to be using it a lot. Right, so your first task was to take this and to sort of change it so that it no longer holds 0 terms. How's that task going? Okay, so essentially in here, you should just be holding some type of ordered list, right, where if a new term comes in, you need to sort of insert it into that list somehow. That's what this popping and pushing is sort of helping you with. Ideally, you want to use a heap. That's going to be the fastest, but it's not like totally necessary. But this is why you're using the push and pop nomenclature in the first place. Like this comes from the heap. So then we have some constructors down here, this x poly. This is really useful because it allows us to define polynomials in like a more natural way. So I can say something like x squared. I hate how this works. Where did it go? Here. Okay. So there was a question about if you passed to the polynomial constructor like a list with terms of like duplicate degree, that would sort of screw things up. And that would sort of gave a response like, oh, this is actually not the implement, like this is not part of the user-facing design. Like what you're doing is like reaching through the abstraction barrier. Is anyone familiar with that terminology? We expect users of this polynomial structure to define things like this. And thereby it would never be possible for them to actually like put in duplicate terms into the polynomial, because when we do this, the addition should already be handling, right? Merging these things when it goes in, right? So you would never at this user level define a polynomial by giving it a list of terms, right? We anticipate our user would use it like this. So just keep that in mind. Why is this in here twice? I want to skip that. Okay, so now we have to start talking about like all of the arithmetic. So I gave you a new set. I said, here's a set. It's all of these polynomials. And now it's incumbent on me to say, well, this set actually forms a ring, and this set actually forms a Euclidean domain and an integral domain. So what do I have to do? Well, first I have to show you there's an addition defined over it, that there's a multiplication defined over it, and that we can get the Euclidean domain out of it, or the Euclidean algorithm out of it. So let's do that. So how do we add two polynomials together? Well, this is essentially just like taking the two polynomials and merging them, right? So what you want to do is you want to look at the leading terms of the two polynomials that you're trying to add. And if they have the same degree, you just want to add them to, you want to merge them, right? So it's kind of weird here that I'm defining polynomial addition and using addition in it. But what I'm actually doing is defining polynomial addition by exploiting term addition, right? So we can define addition on terms and then like utilize that to define addition on polynomials. Okay, so this is the merge term, and just be careful when you're working with your sparse polynomials, because if this becomes 0, you're going to have to do stuff about that, right? That's a problem, right? Because you don't want to insert that. You need some type of if statement to capture that and throw it away if that's the case, right? So that's a degenerate case. So we add these terms together and we just say term plus, and then we remove the leading terms from both A and B and recurse, right? So like you can't really implement this like without making some changes, right? Mathematically, this is okay. I can say this is 0 plus this if that term happens to be 0. But when you're implementing it, that's going to be a problem. So just take care. Okay, if the degree of A is bigger than the degree of B, right, then I just pop off the leading term from A and do that addition. If the converse is true, then I just remove the leading term from B and do that addition. Like the relevant thing is here is that when we make these recursive calls, something has to be descending. I don't know if anyone took my Com 3400 class here. Oh, so we talked about this a lot, right? Bottoming out. So what is the thing that has to go to, like, what is the thing that we're pushing down? The degree, right? So eventually the degree is going to hit 0, right? Which is going to form our base case, right? So the relevant thing here is that this is going to make a call where the sum of the degrees of the input is going to be strictly less, right, than the call that made it. And eventually it's going to descend, right? So it's going to be a valid recursive algorithm. Okay, so here's how we're going to sort of, this is how addition is implemented in your project, right? So we basically did it by utilizing or like just encoding what I said here. We don't really say what it means to add two polynomials. We eventually do that. We sort of have to say how to like add the smaller things to a polynomial. So how do I add like a polynomial, a term to a polynomial? How do I add an integer to a polynomial? Right? And then once I have those things sorted, then I can say, here's how you add two polynomials together. And I say, okay, so to add two polynomials together, just continuously add, right, terms of the one to the other. Right? And since I already defined how to add a term to a polynomial, we can take that and extend it to like a definition for adding two polynomials together. So again, in effect, adding two polynomials together has been reduced to adding terms repeatedly to a polynomial. Right? So all we need then is to add a polynomial and a term. And then when you're making your changes, just be very careful about what happens when you're merging and you're producing zeros. I've already seen quite a bit of bugs emerge on the EdStem for like not accounting for that. That's going to be the tricky case. Like especially when we start reducing things mod p, because they might not be 0 until we do the reduction. Some other things here. Currently, when you write a polynomial like this, if the constant coefficient has this weird behavior, if you want to have a negative constant, you have to wrap it with brackets. So one thing Yanni wants you to do is go in and fix it so this doesn't break anymore. So like if you see if I do this, it should be fine. But if I wanted to do this, oops, no mas. Right, so that's going to just require a little bit of a, just search for this edge case and try to deal with it, right? Okay, so you see that we have, whoops, addition. So that addition sort of, like it's easy conceptually, but there's tricky edge cases. Right? So just be very, very careful about what happens when you add two terms together and they become zero. Stuff will have to be done. Okay, multiplication. So here's like a really easy way that you can define multiplication. So give me two input polynomials and just like cut them however you want. Right, so just suppose you give me A and B. We just make sure that the inputs aren't zero, and we make sure they're not individual terms, because if they're individual terms, then we've actually just have to do term times polynomial, right? Or polynomial times term. So by the time you get to a line 11 here, we're sure that A and B are both polynomials with multiple terms. I'm saying just take them and divide them up however you want. Right, so take A and just write it as A1 plus A2, and take B and just write it as B1 plus B2. This just ensures that you're not doing any sort of trickery, right? That you're not like, putting zero terms in or like breaking apart things. Like you can't have x squared in both. Right? If you had 2x squared plus 1, you can't break it up as x squared and x squared plus 1. You have to keep similar terms together. So you just take the two polynomials, you break them up in whatever way you want, and then you just exploit the distribution property. And so you study this, right? If A1, A2, B1, and B2, right, are all smaller than A and B, then all of these products are going to be products on stuff that are smaller, right? So this recursive call is going to be on all things that are smaller, right? All of the degrees of these calls are lower. And that's all we need when writing a recursive algorithm, to ensure that the input is like strictly less at the recursive call than the input was. Okay, so the way that we've defined multiplication in your project is exploiting this, but maybe in like this sort of, yes, sir. Could A1 and B1 still have the same? Yeah, in fact, one of them is guaranteed to have the same degree as A and B. Yes. Okay. So yes, but you are correct. There's two measurements that we have here. They're degrees and like the number of terms. And you are absolutely correct to say yes, right? And the other one is going to trigger this condition. Right? Eventually, we're just going to be holding one term. And we know how to multiply two terms together. Right? That's handled by the term arithmetic. But that's a very good point. Thank you. So we sort of implemented this in like the silliest way, and sort of like cutting it in half. We're just saying let A1 be like the leading term and A2 is the rest. Let B1 be the leading term and B2 be the rest. Or it may actually be even sort of a little bit sillier than that. We just have to define what it means to multiply a polynomial by a term, or a term by a polynomial. So we're saying just for every t in P1, just keep adding t times P2. This is like sort of distributing, right, all of the terms of A, right, over B, essentially. So that will work, but this is like not a very fast way of doing this. This is like, if you were to cut the polynomials in half better, you'd be exploiting divide and conquer a lot more effectively than you are doing it here. But we're not going to be doing it either way anyways. I want to show you how to do it with CRT. But if you wanted to do extra optimizations to your multiplication algorithm, you could consider doing that, like cutting the polynomials in half better. Okay, so we have addition, we have multiplication, and in order to be an integral domain, right, I'm just trying to like establish that the polynomial ring is going to be a Euclidean domain. It first has to be an integral domain. So recall that an integral domain is a non-zero commutative ring in which the product of any two non-zero elements is non-zero. So like zeros cannot magically appear. When that holds, then the following properties also hold. It has to be the case that the degree of A and B is equal to the sum of the degree of A plus the degree of B. The leading coefficient of A and B is just the product of the leading coefficients, sort of obvious. The leading monomial of A and B is the product of the leading monomials, and the leading terms of A and B are the product of the leading terms. Like this is trivial to work out, right? You just take a general A and a general B, you multiply them out as you normally would, and you can just like what's free from this is that you know absolutely what like the leading term is going to be. It's the product of the leading. You know absolutely what the constant term is going to be. How would you, what would we need to get like the rest of the terms? Yeah, you'd really have to work this out. Like binomial expansion is not going to work here because we're not taking one thing to a power, but this is sufficient just to get the leading terms and the constant terms. Okay, so this is what you need to pay attention to now because this is explicitly one of your tasks. So this multiplication algorithm is going to be really slow, right? Because especially when you convert it to using big ints. Like, so one of the tasks in your project is to show what happens with overflow, right? Because technically the multiplication that you have currently works mod 2 to the power of 64, or like, I guess that depends on the architecture of your machine, but like, I doubt anyone has a 32-bit machine anymore. Okay, so this is going to be the sort of technology that's going to allow you to use machine arithmetic and then do a one-time calculation to like extend that machine arithmetic to big ints. So we're never actually computing with like big ints, we're computing with machine ints and then using this technology once at the end. Okay, so I have to define a few things. So if I give you a polynomial, the height of this polynomial denoted by these these absolute bars with infinity. Are you familiar with these like n forms? Yeah, so this is like the inf form, something like that. But in any case, it's just the largest of its coefficients of absolute value. And so for instance, the height of 2x squared minus 5 is 5. And furthermore, let hash a equal the number of non-zero terms of A. So the number of non-zero terms of this is 2. If we intend to use the Chinese remainder theorem to calculate the product of A and B in ZP, we need an M. So we need to use as many primes so that the product of those primes is in excess of 2 times the height of C, where C is the product. Okay, so how do we get the height of C? Well, we can't really until we do the multiplication, but I can bound C for you. Okay, so here's the bound of C. So if we have A and B, and they're both polynomials with integer coefficients, the height of C is bounded by the products of the height of A and height of B multiplied by the minimum non-zero numbers of A and non-zero numbers of B. So this is important, right? Because I'm going to say we're going to do Chinese remainder theorem. We're going to do multiplication by instead doing multiplications over some mods. But then the relevant question becomes like, well, how many of them do I have to do until I'm assured that like the answer is going to be the same as the answer over like the natural integers, right? So in this original Chinese remainder, like eventually you're going to like solve it for like such a preposterously large prime that the image you get back is the same as the original guess, right? If like the original number was 19 and you were using it, you found the answer mod 101, it's also going to be 19 mod 101. Right? So we need some mechanism to make sure that we're doing Chinese remainder theorem so that the answer we get back, right, the answer that we're looking for is like in the set, right, in the finitely many numbers that we're calculating with. And then once we know that it's in it, it's actually the answer over all of the integers, right? So this is the important part, right? That the product of those primes has to be at least height of A, height of B, minimum times the minimum number of non-zero elements of A or B. And we can sort of see why that's the case. If you just look at A and just imagine every coefficient is alpha, like its biggest one. And imagine you have B and every coefficient is just the biggest, right? It's B, right? You know the height of A is alpha and you know the height of B is beta. If you just sort of do like a worst case analysis here, of like how, like what the largest coefficient is going to be. Like this is what's going to come out of it. It's not too hard to work it out. Okay, so here's a real example then of what you're going to be doing in your project. So I'm saying we want to multiply 3x minus 4 by 6x plus 5. And that ends up being 18x squared minus 9x minus 20. Like that's the product when you actually distribute it out. Okay, so, but if you were to do this naturally, you're using big ints and it's slow. Right? Or at worst, if you were to do this now without using big ints, you get overflow and you get the wrong answer. That's even worse. So what we're going to do is you're going to take this product in smaller classes, like using 5 numbers, using 7 numbers, using 3 numbers. And I hope you can understand how like working over mod 5 is going to be faster than working over like all of the big ints, right? We only have 5 numbers. How slow can it be? Okay, so mod 5, 3x minus 4 is 3x plus 1. Right? Minus 4 mod 5 is 1. 6x plus 5 mod 5 is going to be 1x plus 0, where we're just reducing all of the coefficients mod 5. And then the product here is going to be 3x squared, that's 18 mod 5. Minus 9 happens to be plus 1 mod 5, and 20 is 0. 5 goes into 20 cleanly. So you don't actually know this column. This column is, well, sorry, you can generate this like you just do the multiplication, like using the method you have now, right? Because you can do this without big ints, right? You can do this with machine ints. Or you just, as long as P1, as long as these primes aren't big, as long as they're less than 2 to the power of 64, you're going to be performing machine multiplications while doing this. That's fine. That's fast. Do not do big int arithmetic here. That would be pointless. Okay, so that's the first step, right? You need to have a multiplication algorithm that can multiply polynomials together, but you need to be reducing their coefficients modulo some prime. So you do it maybe for 5, you do it for 7, you do it for 3, and it turns out 3 times 7 times 5 is bigger than 48, which is equal to the height of A times the height of B times the minimum of like their non-zero terms, right? Which is the threshold by which we know if we do CRT, these are the answers modulo all of the integers, right? Not just like the finitely many integers that we're using. So this is how you exploit this. So basically, like, so how can we get an answer? Like, what is the product mod 3 times 7 times 5? How can we get that? Pardon me? CRT. Yeah, on what though? Because we don't really have a CRT on polynomials, right? I've given you Chinese remainder theorem on integers, on the coefficients, right? Because I know mod 5, the sort of leading coefficient is 3. Mod 7, the leading coefficient is 4. Mod 3, the leading coefficient is 3. Well, that's just Chinese remainder theorem. So I can utilize Chinese remainder theorem to get the leading coefficient mod 3 times 7 times 5, which is actually just the leading coefficient mod the integers, right? Because we've passed that threshold. And then we look at the linear terms. We say, okay, the linear term mod 5 is 1, mod 7 is 5, mod 3 is 0. You do Chinese remainder theorem again, and then you extract the linear term, right? Mod 3 times 7 times 5, which is actually the linear term over all of the integers. And then you do the same thing for the constant. Okay, so suppose you've defined this function, right? This Chinese remainder theorem function, where you can give it the images, right? The reductions and all of the things you're reducing by, right? So these are the UIs and these, I guess, for the M's. So if we look here, so I put in 3, 4, and 0, and you get 18. You put in 1, 5, and 0, and you get 96. And you put in 0, 1, and 1, and you get 85. There's a little bit of an explanation here about the symmetric mod, right? Because notice here that we actually are going to want negatives back. Right? So the final step here is you should be saying, oh, I actually generated a solution with mod. I just need to do a symmetric mod here to like regenerate the negatives. Okay, so it turns out that 96 symmetric mod is -9, 85 symmetric mod is -20, right? Symmetric mod 3 by 5 by 7. So here's the product mod 105. And then there's the product once I switch out the numbers with the symmetric mod. So that's the answer. That's the product over the integers. So do you see what you have to do here? You have to do a bunch of multiplications of the polynomial among small primes. Right? Enough of them so that the product of those small primes exceeds some threshold. And I've given you the threshold. Once that's done, you use Chinese remainder theorem on like each of the coefficients to generate the coefficients over the integers. And that's the answer. Right? So we've done, like, how many big int operations do we need to do? Well, only when we're like constructing this last one, right? Moving out. We don't really need to do any big integer evaluations. Like aside when these primes start exceeding like machine integers, maybe then you'll start doing big ints. Right? But only once at the end, right? You only have to do big integer operations to like reconstruct the answer. Like none of these intermediate multiplications actually required any big int calculations. So you should ask me questions about this because you have to go home and like implement this. And I forgot to give you a break, so maybe I'll let you out 10 minutes earlier if that's okay with you guys. Okay. Not really. For factoring, this gets a little bit more messy because if your leading term vanishes, that's a problem. But not here. I suppose you could get really unlucky that, oh no, you can't get unlucky here. So you should be choosing smaller primes, although it doesn't really matter because machine integers work up to 2 to the power of 64. Right? So like working over mod 3 or mod 7, like you're not going to get a performance gain. It's all just machine arithmetic. So maybe it's better to start choosing larger primes so you have to do less reconstruction in the end. Right? Or you can do less of the products. So I suppose maybe, yeah, there are optimal primes. Choose like the previous prime from 2 to the power of 64, and then choose that previous prime. Right? Because you're definitely going to like exceed the threshold. But you should play around with some of this stuff to see like what you can't eke out. That's a really good question. I'd have to know much more about like the finer details of how like Julia is actually implementing some of these things. But either will work. Right? Either you start with like small enough primes, or you can like choose big enough ones, so that like you've exceeded the threshold. But the point is, you need to do multiplications using the machine integers, and then utilize Chinese remainder theorem to like reconstruct the big int solution. Yeah? You're gonna go home and do this? Okay, we can talk a little bit more tomorrow. Okay, we're not really expecting you to, so here's the pseudocode to do it. And so you don't even really have to like take that theory and implement it. You just have to take this like pseudocode and implement it. But there's some details that we have to go over here. So like you may be tempted to like do this as like a vector, right? To take 3 of these and to do Chinese remainder theorem and 3 of these. That's going to be bad. But some of these polynomials may be big. Right? So you don't necessarily want to like do all of the products ahead of time and then like generate the answer. Right? Can you understand how that's going to like require a ton of space? Right? If you need one product for every prime, if you're actually storing it, that's not the greatest idea. Like what you want to do instead is like do Chinese remainder theorem 1 prime at a time. Right? So you may have an answer mod 3 and mod 5, and that will give you an answer mod 15. And then you should like get the mod 15 answer properly. And then you do the next prime, right? Mod 7, and then you get an answer mod 3 times 5 times 7. Right? The only thing that has to be true in Chinese remainder theorem is that the m's have to be coprime. Right? So it doesn't matter that the first one is a composite. Right? It just matters like that the new thing you're adding is coprime with that. Right? So you won't get a performance gain if you do all of the multiplications ahead of time and store them. Right? You just want to do like add 1 at a time. Right? So this is the algorithm or pseudocode for like adding 1 at a time. Right? So here we need input A and B and N and M such that A is a polynomial with integer coefficients using the integers 0 through n. Right? There's no prime requirement here. And you want B so that you're using all of the integers 0 through m. and the only requirement is that they're coprime. Right? So in this context, n is always going to be some product of primes, and m is going to be a new prime that's like not one of the previous list. It just has to be coprime. And then you can go ahead and implement this, right? This gives you the one-step CRT. So here's the pseudocode for like doing the CRT multiplication. You give me an A and a B. These are your input polynomials, and you're seeking the product over like the integers, right? Integer coefficients. And what you want to do is you want to output their product, right, over the integer coefficients. You have to get their heights. That should not be a problem, right? You just scan the coefficients, you look at their absolute values, you pick the largest one. This is the bound that you're going to have to exceed, right? So 2 times height A, height B, and the minimum number of non-zero coefficients. I'm not even really counting the non-zero coefficients. I'm just taking the degree. Do we agree that's just going to be bigger, right? It's a less sharp bound, but like it saves you from having to go and count the non-zero coefficients. Here, I actually recommend that you start at 3. I'm not doing this sort of walking backwards, but implement it like this, and you can go ahead, see what kind of effect it has if you like change this initial prime. And then m is the thing that eventually has to exceed b by like, we're going to continuously keep multiplying it by a prime. So we have c, and that's going to be a times b mod m, right? So at line 11, you have to call out to some multiplication algorithm, which is working modulo p. Right? I think that was like explicitly one of your instructions, right? To create a polynomial structure, which has it baked in that it knows that it's like a polynomial whose coefficient should be reduced mod p. Yeah. Okay, so then you do your multiplication, in this case in Z3, and then you just run this while loop, which is basically saying, well, the product of your m's, like these primes that you're collecting, it does not exceed b. You have to keep adding another polynomial through this Chinese remainder theorem, like this adding one. Right? So generate the next prime. This is actually in Maple. This is a really useful function. I would implement it. By given a prime p, get the next prime. You probably should just do this ahead of time, like just generate a file or something with a bunch of primes, because it may be hard. Like finding primality testing is difficult. First, search through the docs to see if Julia has this next prime function. I'm not sure that it does though. Okay, so you generate an x prime, then you find c prime, which is the product in this new prime, and then you just do one of these steps of CRT. Right? You have your answer mod m and your answer mod p, and you want to use this single step CRT to get your answer mod m times p. Right? And the only thing that matters is p and m are coprime. And then you can increase your m. So just implement this pseudocode, but you need to understand a little bit of the theory, because if things go wrong, you sort of need to understand why things are going wrong. But it effectively comes down to like implementing this pseudocode. Or the final step here is just returning the symmetric mod, right? Returning the negative coefficients. You also could just do everything using the symmetric mod, right? Period. So you never have to do these conversions. That may be a little bit cleaner. In Maple, you can actually turn it on and off. You can say, instead of doing mod, do symmetric mod. Right? So you can do the same, may make things cleaner. So you have to implement this, and you have to implement that. So give that some thought. And again, like I know I may be going very quickly because I need to get through all of this by tomorrow. But again, on Monday, like once you've gone home and thought about this and said, hey, he said something stupid, or I don't understand this, we can have another discussion on Monday. And if you like go to the Abstead and say, hey, can you like produce a bunch more examples? Go ahead. But this should be your tracing example, right? Like this is why I put that there, so you can use it for tracing. Okay, so we've done addition, we've done multiplication, and now we need to do division. Okay, but we don't really do division. What I mean by division here is we need to generate like an integral domain, which means we need, for these polynomials, a remainder operation and a quotient operation. Right? We're not really going to get division the same way we didn't get division over the natural numbers, right? Because the polynomials certainly aren't going to form a field, right? I can't take 2x and divide by x squared. That's a rational coefficient. So like making polynomials a field is off the table, but we can make the polynomials a Euclidean domain and an integral domain if we make the coefficients from a field. So consider the following operation. Like I can, like some of the polynomials, or at least some terms, do allow for division. Like we can divide some of the natural numbers. Like 4 divided by 2 gives you 2. That's division that's closed over the naturals, but 2 divided by 4 doesn't. That's a half. And so the same thing is true of terms. If you have a term where the numerator has greater the degree than the denominator, you can perform that division, right? So x squared divided by 2x gives you 1/2 x. Okay, but I'm saying that our polynomials have to have integer coefficients, and 1/2 is an integer coefficient. But what we've been doing is saying, okay, don't use all of the integers, use some of the integers. And in fact, use a prime many number of those integers, because if we use a prime many number of those integers, that's actually a field. Okay, so instead of saying do this in zx, if I said divide x squared divided by 2x in like mod 7, right, then this is going to be 1/2 mod 7. What's another way of saying 1/2 mod 7? What does it mean to divide? What's another way of saying division? It's the inverse, right? So this is like saying x squared divided by 2x is congruent to the inverse of 2 mod 7x. Oh, that's exactly what I'm saying here, right? So x squared divided by 2x is congruent to 1/2 x mod 7, is congruent to the inverse of 2x mod 7, is congruent to 4x mod 7. So you see, if we now this is okay, right? We can do term division, provided that we're working, providing we're restricting the coefficients to a field, a very particular one, like this integer field of prime characteristic, and the numerator has to be bigger than the denominator, right? We can't do the converse, but that's going to be sufficient for generating a quotient and a remainder algorithm. Let's just look at synthetic division again, and I did some examples here. Okay, so this is back to probably high school, at least calculus. So remember when we could say something like take 10x squared plus 4x plus 1 and divide that by 5x minus 3. So, but I'm going to throw in this caveat that we're doing this in Z mod 11. Right, all of our coefficients are going to be reduced modulo 11. So 5x minus 3, right, is actually congruent to 5x plus 8 mod 11. So what we're actually doing is taking this 10x squared plus 4x plus 1 and dividing out by 5x plus 8. And what the division algorithm should give us is a quotient, this thing, and a remainder, that thing in red. So what is the objective here when we're doing division? The objective is to find some term of the quotient so that when we multiply that term by the leading term of the divisor, we are definitely going to get rid of this. Right, that was the strategy, right? So here, this is kind of easy. I need to get rid of this 10x squared. So what do I multiply 5x to get rid of the 10x squared? Well, 2x, right? So 2x, 5x gives you 10x squared, and then you get 16x, and 16 is 5 mod 11, so that's 5x, right? Then you subtract, it gets rid of this, and then you get 4 minus 5, which is minus 1, which is 10 mod 11, that's 10x plus 1. Okay, now we need to do it again. How do I get rid of this 10x? Well, I have to multiply this 5x by 2. What's another way of saying that? Well, I need to take this 10x and divide by 5x, right, which is exactly this term arithmetic that I was showing you on the slide before. And then we reduce, and we get the 7 back. There's nothing that we can do about the 7 because it has degree less than or equal to what we're dividing out by, so there's the remainder, right? And thus we can say 10x squared plus 4x plus 1 is congruent to 5x plus 8, 2x squared plus 2 plus 7 mod 11. Okay, let's do a more complicated one. So let's divide 5x cubed plus x squared plus 2x plus 6 by 3x squared plus 1 in Z mod 11. So I'm going to write it like this, right, just to make it more clear. So here's a 3x squared and here's a 5x cubed. So what do I have to multiply 3x squared by to get 5x cubed? Well, we could still write, I have to multiply it by 5/3 x, right? Because these 3's are going to cancel, and I'm going to be left with the 5, which is exactly the coefficient that I want to eliminate. But we don't really have fractions. but that's fine because a fraction in this instance is just interpreted as we don't really have a denominator. That's an expression to say multiply by the inverse. Like this is really saying 5 times 3 inverse mod 7. And it happens to be 4x. Right, so this term here is going to be 4x, and it allows us to do the same type of removal, right? We're always trying to remove this leading term, right, when we're dividing out. This is what they taught in synthetic division. Yes, miss. Okay. No, that's fine. Okay, so what's 3 inverse mod 7? What do I have to, okay, so this is going to be hard to do in my head. So 3 times 2 is 6, which is minus 1. And squaring that gives you 1. That should help me do the inverse. Well, we can just count. 3, 6, 9, that's 2, 5, 8, that's 1. So that should be, okay, the inverse of 3 is 5. And then, so that expression is then 5 times 5. That's 25. Mod 7 is 4. Yeah, so you have to see this as 5 times the inverse of 3, right? Mod 7, the inverse of 3, mod 7 was 5. 5 times 5 gives you 25, and then you reduce mod 7, right? And you're generating these inverses how? The extended Euclidean algorithm. Yes, yes, okay. And the same thing is true over here. You would never really write this in your system. I'm just saying, like, this is basically what's happening, right, behind the scenes, right? You'd never really have the opportunity of writing 1/3, right? This would have to go in as 3 inverse, but that's the objective here when doing division, right? To generate 4x plus 5 as being the quotient, and your remainder is 5x plus 1. Okay, so I just say that because this is all that I'm really expressing here in this division theorem. Right, so remember the goal again. I'm trying to establish that the polynomial ring with coefficients that are a field is a ring, well, as a group, is a ring, is a integral domain, is a Euclidean domain. We've already done what? Established that there's addition, established that there's multiplication. So now I need to establish that there's a quotient and remainder algorithm, which is exactly what this is. So the division theorem in, so this is the polynomials with coefficients over a field. You have A and B, which are polynomials with coefficients over a field. B can't be 0. You're not allowed to divide by 0. It blows up the internet. Right? Then there exist unique polynomials, Q and R, quotient and remainder, such that A is equal to BQ plus R is equal to 0, or the degree of R is less than the degree of B. This is just the division algorithm for polynomials. Right? So by saying that this is a theorem, and then by proving that such a thing exists, by giving a division algorithm, right? Now I can say that we have a Euclidean domain, right? Fx is a Euclidean domain because I provided addition, multiplication, and remainder and quotients. How much time do we have left? How much more do I have to do? Okay, maybe, okay, so I'll just show you. We haven't done any of the uniqueness proofs. Let's just do one of them so I can show you how they work out, okay? So here's the division algorithm, but that's essentially what we just did in those examples. The relevant part is this, right? This is the factor that you have to multiply the numerator by to ensure you're like eliminating the leading term of the divisor. This is something called a syzygy in more general terms. So I think this is already sort of implemented for you. Not much has to be done here in terms of your project, but you will generate a quotient and a remainder algorithm. I think, yeah, it's just in there already. You may have to modify this a bit because, so do you understand now why we couldn't write a division algorithm for you? So the polynomials that you were working with, like, presume integer coefficients. I can't do any type, I can't perform the division algorithm until the coefficients form a field. So I can sort of say, I can like prep this remainder and quotient for you, but I can't actually perform it until you like tell me what like residue class you want me to work over, until you like make the coefficients here a field. So this isn't exactly the cleanest interface, right? To say divide P1 and P2, and I'm going to give you back a function which will give you like the division once you give me a prime. It's like, so one of your tasks is to sort of like make a cleaner interface, like have some type of polynomial that's aware what its coefficient ring is supposed to be, and to automate all of the arithmetic so you don't have this strange behavior. Because this may be a problem too in your like Chinese remainder theorem. You have to have these like, you want to do a arithmetic mod p on your products. So at that point, it's already better probably to be using the polynomials that work over mod p, right, in that. Okay, so one uniqueness proof, right? Just so we can say that we've done one, right? Because the statement here for division say not only can I generate the quotient and the remainder, but the quotient and remainder have to be unique. So this is not constructional anymore. The construction is for the existence. These uniqueness proofs return to like how we're used to in math, where we just assume that it isn't unique and demonstrate some type of contradiction. So what's the contradiction here? Okay, suppose I have A and B, and there are two different unique quotients and two different unique remainders, right, towards a contradiction. Okay, so that means, right, that B times the first quotient plus the first remainder is equal to B times the second quotient plus the second remainder, right? That's the property, like that's the division property. Okay, well, if this holds, we just move stuff around. And this says that B times the difference of the quotients is equal to the difference of the remainders. Okay, but if this means that B divides the difference of those remainders, yeah? Okay, but the remainders have a property that they have to be less than the degree of B. Like that was asserted in the theorem. Okay, so how can B divide the difference of two things if the thing that is dividing has less degree than it? There's only one scenario where that's the case. Well, like suppose B has degree 2, right? And this has degree less than it. But I'm saying like we're asserting the truth here. We're saying B does divide the difference of these R's. So what do we know? Like what's the only thing B can divide? 0. Okay, so this means that the difference, like this here has to be 0, which means the remainders are the same. Okay, well, if the remainders are the same, you just do some more arithmetic, and you'd also deduce that the quotients have to be the same in the following way. So if these remainders are the same, that means that this is 0, and that means that this is 0. But that can't be the case because we're not working in a, like this is an integral domain. We've already established that. And integral domains can't have 0 divisors. Right? So utilizing the fact that we can have 0 divisors, like this has to be unique. Right? Otherwise, the original thing isn't an integral domain. So that's how you can get one of the, this is one of the easier uniqueness proofs. Some of the other ones can get quite hairy. Like I'm essentially giving you like the 2-hour version of like what I took over the course of a semester, because we absolutely proved every single thing that I have mentioned today in like great detail, which was very interesting, but not really necessary for these implementation purposes. Okay, so there's your division algorithm. There's the divide algorithm as stated in your homework, which gives you a quotient and remainder, but with this weird interface. Like we can only sort of do it once you restrict the coefficients to like a residue class. Here's a worked example. I think last year we had the students implement division, so I wanted to give them like a worked example, but this is essentially like the long, it's just this, right? But I worked out every step of the algorithm in the division algorithm, but it's effectively this. This is all you need to know. Okay, so that we have addition, we have multiplication, we have quotient, and we have remainder. So the last thing that we require now is like a GCD algorithm. And why is the GCD algorithm important? Aside from like helping us solve systems of polynomials. Yeah. We're going to get multiplicative inverses. We're going to be able to find polynomials and another one so that we multiply them to get a unit back. Right? Remember, like we haven't really even hit the thing that I'm trying to teach you yet. Right? Tomorrow is going to be the big punchline, where we're going to take all of this and I'm going to show you how to factor a polynomial. Like none of this really makes it obvious how we're going to factor stuff. Like come tomorrow, I'm going to have to utilize the fact and take for granted that no, like I can get remainders in the following way. I can get products, I can get additions, and I can get quotients, and we can do divisibility testing and stuff like that. Right? Because when we're doing factoring, what is factoring if not finding factors that divide it, right? And how am I going to tell if like f divides g? Well, I'm going to do a remainder and ask if the remainder is 0. Right? So all of the technology that we've developed today is going to be like critically necessary for like the punchline tomorrow. And the final piece of technology that we're going to require is this GCD. Right? So effectively, like I'm really going to go like gloss over all of the details. The same way that you have the extended Euclidean algorithm for integers, we have the extended Euclidean algorithm for these polynomials, like provided the coefficients are a field. And here it is, right? So we can just run it. You don't really have to understand it. You just have to appreciate that all we've been doing was this lecture is taking like the integer version of stuff and creating polynomial version of the same stuff. And it's all the same algorithms. You just have to sort of swap out like integer arithmetic with like polynomial arithmetic and integer modulos with remainders. So just to prove that it works, okay, so here 2x squared plus 3x minus 5, right, minus 3x squared minus 4x plus 6. Why is that sum there? Right, so I'm saying take P1 and P2, just multiply them together and find the GCD of that in P2, right? So you're certainly going to get P2 out of that and do so mod 101, right? This extended Euclidean algorithm has to do division. Right, so therefore we have to give it a prime, and it's also going to have this really weird interface that you have to correct. But here is that's the GCD, I believe, and these are the Bézier coefficients, right? So this was a sort of bad example, I guess, because one of them is 0. But sort of that's where we're going to stop, right? We have the integers; they form an integral domain and Euclidean domain because they provide addition, multiplication, remainder, and quotients. Right, and essentially the Euclidean algorithm. We have polynomials, which form a ring, but in order to get the quotient and remainder from them, we need to restrict the coefficient fields. We need to restrict the coefficients to a field. And we're doing so by only using finitely many integers, right? 0 through p minus 1, where p is some prime. And doing so allows us to find inverses using the extended Euclidean algorithm, right, for integers. Okay, so now we have quotient and remainders for polynomials themselves. Okay. So like really all you need to take from this is the Chinese remainder theorem, multiplication. Like that's the one explicit instruction you have on your task sheet, but just implement the pseudocode that I gave you. And then use the worked example that I gave you. You should probably work out some more worked examples, right? Just so you sort of have a feeling of how it works. But it's essentially just performing integer Chinese remainder theorem on all of the coefficients, right, of those products. So what we're going to do tomorrow is start talking about factoring. And this is like really, really interesting. And we're going to, I'm also going to like cover like the optimizations that you have to do, because one of the other things that's specific in your task sheet is to perform this optimization. Right? So I kept telling you like this sparse polynomial is going to be really important to us. And so that p to the power of k is going to be enormous. So there's some optimization that you're going to have to do to make this power, like I don't want to do x to the power of p to the power of k. I don't want to have to do p to the power of k multiplications. I want to do as many squares as I can. I want to square, right? And then add what I have to do last. So you can actually work on this one as well. You don't need to know factoring to do this one. It's just one of the other like arithmetic optimizations, right? Instead of doing x to the power of k by doing k many multiplications, you can actually do log many multiplications, right, by doing squares. But we'll talk about that tomorrow. Any questions? Okay, so like mull this over, because I know I went pretty fast, but again, it's because like we have to get this all done by tomorrow. So you have like comprehensively all the material to complete the project. And on Monday, we're going to like regather and like talk about this sort of all again. All right. Okay, so I'll see you tomorrow. Bye, chat.
you have any questions before we go?